Okay, hello everyone. For today research trend introduction, I will talk about the survey of recent StyleGAN research in CVPR 2022. So the reason as to why I chose this topic is that maybe because it is too short of a gap between my last survey presentation and this one, so I couldn't really find something interesting to present. So I don't know. I read a lot of recent publication, but nothing really piqued my interest. There are some cool research, but mostly I feel either too few or too sparse to be collected into a summary. So because of that, in the end, I just went to the CVPR site and searched for papers with the word StyleGAN in the title. So therefore, I have this survey of StyleGAN in CVPR 2022. From there, I got four titles. Fortunately, the number is just right, not too few, not too many. The first is SemanticStyleGAN, Learning Compositional Generative Prior for Controllable Image Synthesis and Editing from ByteDance Inc. HyperStyle, StyleGAN Inversion with Hypernetworks for Real Image Editing from Tel Aviv University. HyperInverter, Improving StyleGAN Inversion via Hypernetworks from Fin AI Research. And then the last is StyleGAN-V, a continuous video generator with the price, image quality, and perks of StyleGAN 2 from King Abdullah University and Snap Inc. So, as a bit of refresh, about a year ago, I've talked about StyleGAN and StyleGAN 2 during the paper introduction. StyleGAN is an alternative generator architecture for image generation using GAN, borrowing from style transfer literature. It is automatically learn unsupervised separation of high-level attribute and stochastic variation in the generated images. It enables intuitive scale-specific control of the synthesis, which resulting high-quality, high-resolution generated images. The architecture of StyleGAN is the first StyleGAN is based on progressive GAN baseline and then switch into ResNet style in StyleGAN 2. And then bilinear sampling replacing nearest neighbor, addition of mapping networks, the use of affine transform and adaptive instance normalization inside the synthesis networks, adding noise input throughout the networks to make image more diverse, and then also they add mixing regularization and the addition of adaptive discriminator augmentation. And then also, this is kind of reason why I picked CVPR specifically because both the StyleGAN and StyleGAN 2 also from CVPR. So that's why for the CVPR 2022, I try to find what is the update from here. So last year, I also mentioned about this feature entanglement in StyleGAN, which is that ideally we want the latent code as a code that encodes the feature that we want to appear in the image, something like there is a code for eye color, skin color, hair length, and so on, right? But in fact, the features are still entangled, so everything is mixed up into one vector. And so attempting to tweak the input even a bit, it will affect multiple features on the image at the same time. So that is the problem which this first paper tries to tackle. The SemanticStyleGAN Learning Compositional Generative Prior for Controllable Image Synthesis and Editing. The idea of this feature entanglement was these mapping networks in StyleGAN, right? The latent codes are highly informative but also difficult to interpret. Synthesis procedure is usually stochastic, randomly from noise, and no user control is naturally promised. And then StyleGAN mapping network introduced to create an untangled feature that are easy to render. But in practice, the mapping is based on resolution, so it can entangle between coarse, middle, and fine feature, but they are still not specific about which part of coarse feature that is affected by the feature, which middle style or which fine style specifically that is changed if we change this feature code. For example, here if we just want to change the coarse feature or the big feature, then the whole image is changed. That is the limitation of controllability of StyleGAN, which different attributes could be correlated in StyleGAN. Unexpected attributes or local parts are changed while we want to edit a certain attribute and area. So for this example here, because the feature is oriented like this, right? It is tied with the specific resolution during generation. So for example, in this, we want to edit the bang of the hair from this picture, although it is achieved, but other feature like the beard, the hair is also changed. So we want to only edit this part, but everything else also change. This is because the feature is oriented like this. And so here they introduce semantic style GAN. It is a model that tries to generate prior for controllable image synthesis. It is factorized based on semantic parts defined by semantic segmentation masks. So now the output of the generation is not only the image but also a max of which part the latent code is intended to. And so different semantic region can be controlled separately. So now the orientation of the latent code is going to be like this, where we have actually specific type of feature in a specific place of latent code that we can control. And that is the semantic style GAN. This is the whole frameworks. So I will go step by step for the training process. So the first step is similar to style GAN, where we start from noise factor and we use mapping networks to generate intermediate latent codes for each resolution, similar to mapping networks from style GAN. But then in here we have another networks, which is a local generator. The local generator will generate feature map, this one, feature map and pseudo depth map from each semantic region. So there are many local generators for each resolution. Each generator will create feature map and pseudo depth map. And then after that, we combine the pseudo depth maps by using softmax. We fuse the pseudo depth maps and then we create this coarse segmentation max. So from here we will know which feature will correspond to which code corresponds to which feature. Is it the hair? Is it the face? Is it the mouth? And everything. And then from here we use the max, also the core segmentation, to composite the global feature map. We fuse the feature maps and then use the core segmentation to get a composite feature map like this. So we will know the combination of the global feature map. And then both the feature maps, the combined, the fused feature map and the fused segmentation max, we upsample the feature map. So we put the feature map into this generator, the render net, to generate the new generated image, the fake images. And then we also use the feature from the render net to upsample the masking, the segmentation max into the same resolution. So now the output of the generator is the fake images and then the segmentation max that correspond which feature of the image. And then from here, the discriminator is similar to the original style GAN discriminator, but it receives two input images. So it is a dual branch discriminator for RGB image and segmentation max pairs. So it receives fake image and the new segmentation max of the generated one, and then we provide the real image and its target segmentation max. And then from here, the discriminator will be trained to determine whether this pair is fake or real. And so yeah, that's it, the training procedure. The model architecture, the mapping network is the same. It is 8 layers of multi-layer perceptron. The new model is local generator, which is just a 1-by-1 convolution, 10 layers. It has input of Fourier features for the positional encoding. And then for each local generator, it has two outputs, which is one to output the pseudo depth map, and then this in here to output the feature map. And the RenderNet generator is the same as StyleGAN architecture, but it has modified so that it can be used to input feature map at 16 by 16 and 64 by 64 resolution, and also it is the output is used to upsample the coarse segmentation max into the high resolution segmentation max. And then this is the discriminator. It is the same residual blocks, but it one receive RGB image and one receive the segmentation max. And then it sum the output and calculate the standard deviation and use FC layer to determine whether it's real or fake. And the training, the 256 by 256 model is trained on 432 gigabytes of Tesla V100, and then the 512 by 512 model resolution model trained on 832 gigabytes of V100 GPUs, trained about 2.5 days. But for the inference, it takes only 0.1 second to generate an image on a single GPU. So this is the result. The FID score and the inception score is not better than the original StyleGAN 2, because this is the semantic segmentation is the FID is higher and this inception score is lower, so the quality is not better, but it is comparable. However, with this semantic style GAN, we have more control and editability to the image. We can specifically edit which part of the image using the Latin code. So this is the example of generation model, the high resolution and this segmentation max with the resolution of 512 by 512. And then for the ablation study, they show that the function or the effect of local generators. The local generators helps to determine or to map each Latin code into each type of segmentation max and its feature. So with more local generator edit, we can get more and more segmentation to help generate the image. And then this is the result. When we use this model to generate an image, we can specifically change a type of feature without changing anything else of the image. So for example, here we can change only the hair or the mouth or the eyes without changing any other parts of the image. And then the first row here is also change the shape of the face without changing any other feature, or we change the texture like the skin color and old age without changing any other feature. And we can also see this change in the segmentation max. And also this model also able to adapt to other domains outside the training set. So for example, here with the cartoon face, they still able to produce the same result. And then from there we can, yes, this is the latent editing. We can change real image into specifically what we want to add or change, unlike the StyleGAN 2. And then also this is the example of we can manipulate target image by transferring the latent code from a reference image. So for example, here if we want to change the background based on this reference, we can change only the face of the target. We can change only the eyes and everything. And also, since nowadays a clip guided modification is very popular, so they also show a little bit that they can do this also with clip guided. So they can change feature based on the input text without changing any other features that is not supposed to change. So a person with brown skin, so they only change the color texture without really changing the shape of the hair and the pose and everything. And yeah, that is the first paper of semantic style GAN. Now the second paper with StyleGAN on its title is the HyperStyle StyleGAN inversion with hypernetworks for real image editing. So this is another take on image editing using StyleGAN from Tel Aviv University. The previous research is we make a new version of StyleGAN. So we change the model. But in here, instead, we want to use the existing StyleGAN to edit a real image. So the StyleGAN generation is obviously we changed from latent space into an image. So we can control the image based on the latent code, right? The goal in here is that we have a real image and we want to modify the image based on its latent space. So obviously we need to do what is called StyleGAN inversion. So we need to change the real image into its latent code first, and then we can modify the latent code to make the edit on the image, right? So this is the case of StyleGAN inversion. How to get the latent space of an input of a real image. Now, the inversion technique itself, there are many approach. The first is optimization approach, where we start from random latent code to generate a style GAN, and then we check the difference of this image, and then we optimize, we update the latent code until we achieve the most similar or the best reconstructed image. So for example, in here, the first initial is very different, and then we optimize, we update the latent code until it reach the most similar to the target. So this is optimization approach. It is accurate, but obviously, since it is optimization, it is slow inference because it needs to optimize. So the other approach is the encoder approach, autoencoder, which is we train an encoder, the new model, to map any image from dataset into the latent codes, right? That is specific for the pre-trained style GAN. So yes, obviously it is fast. If we want to get the latent code from the image, just one forward pass, we get the latent code, but it is less accurate. So it yields what is called distortion editability trade-off, where if the encoder is so good to map any image into its correct latent code, usually the latent code, the controllability or editability from the latent code is bad. So this is the trade-off. And then the third approach is the tuning approach. So it is like optimization approach, but we don't only optimize the latent code, but instead we optimize the model itself, the pre-trained model style GAN itself. So the technique is, first we get the closest latent code, for example using the encoder. So we get the latent code. So for example, this is the target. We put this into an encoder, so we get the latent code. So now the latent code, if we put the style GAN, it generate into this image, which is still different from the target. So now we perform optimization process to the model itself, to the style GAN, to the original style GAN. We update the image so that with the same latent code taken from the target, we update the style GAN so that it will generate the better reconstructed images. So, and here we change, we make a duplicate, a new style GAN model that can generate the correct reconstructed image. This is the tuning approach. It is better than encoder, better than the latent code optimization approach, but still, since it is still optimization, so it is still slow. Now, the fourth approach is what is called hypernetworks. So hypernetworks is a neural network tasked to predict the weights of primary networks. It is essentially a network to clone a new model. That is what I get from here. So it is trained on larger data collection. The primary network's weights are adjusted with the respect of specific inputs, yielding more expressive model. So it is a case of tuning generator like the tune approach, but without the optimization process. The idea is like this. This is the whole framework. So the goal is like the tuning approach. For example, this is the image that we want to edit. We want to perform inversion. We approximate latent code from this image. For example, using pre-trained encoder. So we put this into an encoder. We get this latent code. But if this latent code is inputted into StyleGAN, it receives this image, which is still different. So we need to make it better. The goal is that, so this is the actual StyleGAN pre-trained generator. The goal is to create a new model, like a clone, that if we fit this latent code, it will get the better reconstructed, like the tuning approach. But the process from here to here is not optimization process. So it is just one step. The way they do is that first we get the image, and then we get the initial reconstructed image from this latent code. We fit both image into a ResNet backbone. We get this feature map, combination of both images, and then we fit this feature map into what is called refinement blocks. So it will try to basically find the difference of weights that generate this image and generate this image. So the refinement blocks, there are many refinement blocks for each layers of the generator. The refinement blocks will output the weight offset, which is the difference between the pre-trained weights and what the new weights should be for each convolution layer. And then the offset is then replicated to match the kernel dimension of the corresponding layer. Okay. So from here, after we fit the feature into refinement blocks, we get this offset of weights. We update the original weights. So we take the original weights, we apply multiplicative scaling factor using this offset. So we just multiply the weights with the difference. We get the new model. So the same architecture but updated weights. So this is the new model, but it is just one step without iteratively optimize the model. And then if we take this new model now, if we fit the latent code to the original StyleGAN, we get not correct image, right? But if we fit into this new modified generator, then we get this better reconstructed image. So this is the inversion of StyleGAN using HyperStyle. This is the comparison, the input, the initial reconstruction with only encoder, and then this is the final reconstruction using hypernetworks. It shows that the reconstruction results is very good. It matches the inception distance and other L2 distance of the image like the StyleGAN. So this is also the reconstruction results compared to other technique of inversion, which is this encoder based inversion or this optimization inversion. So this HyperStyle achieve better L2 distance and F1 distance between the result and the target. And then from here, we can use the existing modification from latent code using the original StyleGAN 2. So from this original input image, real image, we can change like to make it young, make the hair darker, and so on. And also, it shows that it is able to adapt into other domain that is outside the training dataset. Yeah, that's it for the second paper. Now the third paper is essentially the same. So it is titled HyperInverter, Improving StyleGAN Inversion via Hypernetwork. So it is basically two concurrent research that is both published in CVPR 2022. It is basically the same. So this is HyperInverter. So you can see that this framework is the same. So we have this encoder phase to get this latent code from the actual image, which it will reconstruct not too good reconstructed, but then both of the image will input into this second networks, and then we have these hyper networks to update the new generator so that it can construct the image better. So what is different? The first difference is on the encoder. The HyperStyle, the previous paper, used the existing pre-trained encoder, E2E encoder, which is based on also the previous research PSP encoder, and it is a ResNet backbone of encoder. The HyperInverter, they trained a new model from scratch, which based on FPN networks. The second difference is the feature map. In HyperStyle, they use the easy way. They just stack the image. So they stack the image together, fit into a ResNet backbone to get the feature map. That's it. While the HyperInverter, they feed forward the network separately. So which is actually we can do this stack together and we get the same actually. But they fit separately into the ResNet, so we get the feature map from the initial reconstruction, and then we get the feature map of the target image, and then they use this fusion operator to combine both of the image. So in here it's just stack of feature image 1 and then the initial reconstruction, right? Just the stack. But in HyperInverter they introduce the fusion operator, which I cannot find the detail on the paper, so I don't know what kind of fusion in here, but based on this number, maybe they also just stack it, but I cannot find what is this fusion operation on the paper. So, and that's it. And then the last is the hyper networks itself. The HyperStyle, they call it refinement blocks, which is consists of convolution and fully connected layers like this. In HyperInverter, they call it feature transformer and linear mapper, which is the feature transformer is a convolution and linear mapper is fully connected layer. So just different naming, I think. But essentially, this is almost the same. And then just difference in terminology. The first encoder output, the HyperStyle, use the normal terminology of latent code. In HyperInverter, they call it content code. Output of network, in here we call feature map. HyperInverter called it appearance code. And then the difference weights between the new and the pre-train, the hypernetworks call it offset. HyperInverter called the difference is residual weights. But everything else is the same. It achieves quantitative reconstruction result with inference, which they also compare to the same model of PSP, E2E, and Restyle. The additional test in here that they also add user ranking to check how good it is subjectively from optimization and encoder approach. So they show that their approach using hypernetworks is way better than optimization and encoder approach. And yes, from my perspective, this is not better than the previous one. So maybe yes, the same reconstruction result compared to the encoder approach and this optimization approach. So this is also this editing result. After we get the latent code, we can do the editing process the same as the hypernetwork. This is also, they show the interpolation from one input to another input. And yes, that's the third paper. Now the last but not least, the StyleGAN-V, a continuous video generator with the price, image quality, and perks of StyleGAN 2. So first, about the naming, this is not StyleGAN-5, this is StyleGAN-V for video. So the naming is a bit confusing. So this is the most interesting, I think. So they talk about the current video generator is that a video synthesis or video generator treats video as discrete sequence of image to produce the next image, right? So because the frame, the image is discrete, so usually we have input of several images to generate the new next frame, right? So this is treat video as a discrete sequence of image. And then also the process, usually most of the current video generator use Conv3D based architecture, which is slow to train and very expensive. And then also most only able to generate short video, like about 64 frames in each generation. They cannot generate a long image from this example. Like after 1 minute, the image is just broken. They cannot generate frame longer than just 64 frames or so. And also, if we see about the quality of the image, it is way lower quality, usually a small resolution compared to the image generator. So this is the Moko GAN video generator and DGAN video generator. It shows that after we skip, the longer the video, the worse frame it produces. So what these authors propose in here is that video are a time continuous signal. So video is a continuous data, not discrete. But the current video generator treats video as a discrete. So they in here they want to use the video as intended, which is a continuous. So treat video as continuous signal of xt that map any time coordinate t into an image frame. So if we have a video, right? We have a video, we don't see it as a sequence of image, but we see video as if it is a long stream of data. So each video is a continuous function of xt, which is a continuous in time t. So there is no longer, we don't see individual frame inside video anymore. This is the view that we take in here. And then they employ this neural representation paradigm to perform this generation. So neural representation paradigm is representing continuous signal as neural networks. It is popular for images, videos, audios, and so on. So basically, we train a neural networks, for example in here, which predicts RGB color at any position at time t from any position of x, y. So essentially, we want to create one neural network for each video that can receive input t, and then it will generate frame for any t. So this is just one neural networks to produce infinite frame from this T, because we view the video as a continuous signal. So we can put anything in here. So this is the idea. So that we get this GAN-based continuous video synthesis, which is a continuous time video generator. It is no longer autoregressive model because we don't input frame to generate new frame, so it is not autoregressive. Now the challenge they show here is that they need to develop a new positional embedding, they need to develop sampling scheme, and then to redesign the discriminator. So first is about the positional embedding. So they argue that in video generation, the temporal information for the positional embedding should be aperiodic. Most of the current video generation use sine or cosine positional embedding, which is cyclic, right? So if we use this, then the video will loop, because this we will arrive at the same cosine position eventually. So it is cyclic. They argue that video should not be cyclic. It should be aperiodic because we want the video to infinitely generate it without looping. So they develop a new positional embedding, which is a time varying wave parameter produced by a conv1 dimension model. It is depend on the motion information, so this positional embedding will produce different embedding for different video. So if we just use cosine or sine, then each video will have the same positional embedding, right? But in here, they look at the video and produce the appropriate positional embedding for each video. That is the idea. And then the second is about sparse training. So now, because we see the video as a continuous stream of T, so there is no longer frame to train, right? But to train the model, we need a frame to train. So eventually we need to sample frame from this stream, right? We need to sample frame for training. So first they look at the dataset. They use the forensic dataset, sky time lapse, UCF, the new dataset of rainbow jelly, and face dataset made. They rescale into 256 by 256. So based on the dataset and the statistic of dataset, they say that the frame do not change much in single video. Either it is phase or time lapse. So we can just use extreme sampling. So in each video, we can just sample a few frame without using the whole frame to train the model. So they talk that from the statistic, they conclude that a few frame is enough to get the idea about the entire video, which is essentially like saying that if you have seen 2 frames from this dataset, you have seen them all. Like you understand the whole clip with just 2 frames. And from here, they decide that each video, we will extract only 2 to 4 frames per video for training. So now this 2 minutes video, we reduce it into just 2 or 4 frames per video. So it is extreme sparse sampling. The sampling itself is randomly sampled. So it is not like we sample each after an interval of frame to sample, but we sample randomly, but with maximum interval is predetermined. And then now, because the discriminator, usually for video generator, there are 2 discriminators to check the quality of the image frame and then the whole video altogether. So they need 2 discriminators for video generation tasks, because in the current video generator, the data is video, right? That's why they need image discriminator and video discriminator. But now, although the generator will be able to generate frames continuously, no matter how long the video is, but the real data that is used for training only 2 images per video. So it is no longer a video, it's just 2 to 4 images. That's why we don't need this video discriminator anymore. So we just need image level discriminator. So in this model, they just use 1 discriminator. And then the discriminator is conv2D based because no longer video, so we don't need 3D convolution. They also aggregate the information of temporal information to the discriminator, because the frame, so let's say from video we sample 3 frames, right? But the 3 frames are sampled from different interval. That's why this interval information needs to be incorporated to the discriminator. Because if not, then the discriminator will confuse when this image appear in the time frame. The design is based on StyleGAN-2 discriminator, which is essentially the same, but the addition of this temporal concatenation to embed the distance information. Okay, that's the StyleGAN-V summary. It trains generative model over video signals, having only subsample version. Built on top of StyleGAN, it is efficient and able to produce high quality image. It is able to generate infinitely long video, and because it is based on StyleGAN, it has the same manipulation properties from the latent space. Also, they said that it is the first one of video generator that is trained on 1024 and 1024 resolution. Now, I want to talk about the synthesis process. How can the StyleGAN-V produce the video? So, because this is interesting, I think what I get when I read this paper is it's like when we create the video of StyleGAN interpolation, right? So if we want to create a video of interpolation, we feed 2 latent code, right? And then we just interpolate between these 2 latent codes. So we get many latent codes. We feed into the StyleGAN and we get this video, right? So this is essentially a video, right? Where a video is a recording of moving visual images. But it is not what we want, right? What we want is maybe something like this. We want the object is fixed, but then the object is animated. The object is moving, right? This is the video that we want to generate, not this transition from one object into another object. But it is essentially, I think, comes from this idea. So we know that the StyleGAN has 2 inputs. The style input and then the constant input, which is it is unused, but it is constant. It is still an input. So we know that the style features comes in here, which is it is a pose, hairstyle, shapes, etc., etc. And then if we interpolate this, we get this video. So what about this part? Or what indicates what this input is representing? So maybe if we think about it, maybe this part is having inputs like something like this, like it is a template canvas or a face mask is represented in this constant. So with this interpolation result in mind, if we interpolate this part of constant and then we fix the feature, but we interpolate this part, maybe we can get something like this, right? So this, I think, this is the idea where the idea comes from for this research. So this is the generator model of the StyleGAN-V. It has content mapping. This is the new model. It has a motion mapping, which is the same mapping networks as StyleGAN. And then the synthesis, also the same as StyleGAN, but with slight modification. So to generate a new video, first we generate a content noise. So we generate the object noise of ZC, content noise, and then like StyleGAN, we use the mapping networks to transform the noise into this intermediate latent code of W, which is shared for all time step. So this is the object or the content information, right? Because it will be the same for all time steps. And then we have this content mapping. So for each time step T, for each frame we want to generate, we sample a motion noise, we sample a set of vector, a discrete sequence of equidistant trajectory noise that is long enough to cover the target timestamp. So this is just a random noise. And then we use this content mapping network, which is convolution 1D, to transform first from Z into this U sequence, which is still a sequence. And then from this set of U, we take a pair. So we take pair of token UL and UR, where the T is between them, and then compute acyclic positional embedding. So we create an interpolation of using acyclic positional embedding between this UL and UR, where the T is the time step frame we want to generate. We create acyclic positional embedding or interpolation between these two. So this will create this new phi, which is a motion code. And then because the motion code are continuous at any time step t, so from here we can get any motion code at any time step. And then for every phi, we can tile and concatenate this motion code into the constant input tensor. So like the idea that I talked before. So now we have this interpolation kind of, which is fed into the constant template. That is the motion part. And then the synthesis is the same as StyleGAN, just a slight modification to accept bigger constant input tensor. And from here, by changing the phi, we can generate frame for any time step non-autoregressively. So we can just change the phi and it will generate a new frame for that time step. And that's it. It's very interesting. So it has efficient training because the network is like StyleGAN. So it is trained the same cost as training the StyleGAN for image. But this is for video. It has these almost the same FID with the StyleGAN, which is lower is better. And then the training days is also efficient like training a StyleGAN compared to other video generator model. And this is the result compared to other model with different dataset. They show that their model is better than any other model. And this is the results of video generated compared to DGAN and MocoGAN HD. So we can see here, if we just 1 second generated, all of the model can produce videos, but longer than that, this MocoGAN HD will just break the pixel. The DGAN will just blur into nothing, but this model can stay generate a good face. Also like this MocoGAN for this sky time lapse, they produce still moving sky even after 1 hour. But in MocoGAN it just break, or this DGAN become like this video is like broken, right? It's not no longer moving clouds like this StyleGAN-V. So, and this is also for this if the model is very dynamic, like a UCF 101. So in this phase forensic and time lapse, the object is very static, right? Because it is just a face and the sky. But the UCF is more dynamic because it has people running and boxing and everything. And it shows that although the motion is not really comprehensible what it is doing, right? But it still can generate frame after 1 hour of video generated compared to MocoGAN where it just break after 1 minute. It is also from if we train in high resolution, it can generate long video. Although if we look at this motion, it's just moving just like that. It's not really moving any dynamic movement, but it can generate continuous video. And also they show that they can like using clip to edit the video of the shelf result. For example, in here we can use randomly generated or just like before project the image into latent code, and then we can edit this image into the new edited image, and then we animate this edited image. So this is, for example, projecting image that is not inside the dataset, and then we also use clip guided editing to modify the video. And yes, that's all for research of StyleGAN in CVPR 2022. Thank you. If there's any question,